Welcome to the next lesson, and we are going to look at graphing logarithms and using the change of base formula. So the change of base formula is when we want to evaluate a logarithm that has a different base, and that base is not in 10. The formula we're going to use is log base b of x is equal to log x over log b. So here is our example on how to utilize this formula. So if I want to evaluate this, a lot of scientific calculators don't have the change of base function, so you would only have the regular log base 10 button on your calculator. So if that's the case, we can use this formula to help us simplify this calculation, and then we can use our scientific calculator to do the rest. So if I want to rewrite this in terms of the change of base formula, it's going to be log of 100 over log of the base, which is 6. And then we can put this into our calculator. So if you want to pull out your scientific calculator, we're going to press log 100 divide by log 6, and we should get 2.57. And that's it. So again, we want to use this change of base formula whenever we have a base that is not 10 and we want to find the final answer of it. So we want to evaluate that logarithm. If this is a non-calculated question, it is definitely okay for you to leave it in terms of this or in terms of this. But if you do have a calculator, then yes, you should punch it into your calculator to find the final result. And if your scientific calculator does have the change of base function already, where you can punch in log base 6 of 100, then you can of course do that as well. Okay, we're going to move on to example 1 part B. So if I want to find what log base 3 of 2 is, this is going to be log 2 divided by log of our base, which is 3. And then we can put this into our calculator as log 2 divided by log 3, which is 0.631. Okay, so I want you to try the next one on your own, and then when you're ready, please press play for the solution. Okay, so for this try it yourself, it's going to be log 6 over log 8, and then you can put this into the calculator to find out the final solution here, which is 0.862. All right, so moving to example 2, we are going to graph a logarithmic function. And remember, logarithms are inverses of exponential functions, so it's going to share a similar shape as your exponential function, and it's going to also have an asymptote as well, but it is oriented in a different way. So I'm going to graph log base 3 of x as an example of this, and we are going to describe its characteristics as well. I'm going to start off by drawing the xy plane. And before we would have an asymptote at the 0 line here at y equals 0 for our exponential graph. But in this case, remember when we find the inverses, we switch our x and y values. So this time I'm going to have a vertical asymptote at x equals 0 instead. So a vertical asymptote here. Before, on our exponential graph, we had a point at 0, 1. And if I want to find the inverse of that, it would be a point at 1, 0. Okay, Then if I want to find another point, I can do a table values on the side. So if you want to find, you already found one point, but if I were to verify that I have a point at 1, 0, this would be log base 3 of 1. So 3 to the power of what gives us 1? 3 to the power of 0 gives us 1. That's why I have the point out at 1, 0. The other one I can do could be 3. So log base 3 of 3. In other words, 3 to the power of what gives us 3? 3 to the power of 1 gives us 3. So I have a point at 3, 1 that I can also record. So I can connect these 2 points. For our end behavior, as our x approaches infinity, y is also approaching infinity. So it's going to look something like this. And then because we have this asymptote, we are going to create our curve so it's approaching our asymptote there. So this is your graph of y equals log base 3 of x. Now here's some characteristics. It says identify the intercepts. So we have an x-intercept at 1. We have an asymptote, a vertical one, at x equals 0. Our domain is from 0 to infinity. Remember not to include the 0 because you have an asymptote, and then your range is from negative infinity to positive infinity. So these characteristics here are for all log graphs that have not been transformed. So that means, let's say log base 2 of x, log base 10 of x, log base 100 of x, doesn't matter what the base is, it's going to have all of these characteristics for our logarithmic graph. Now I want you to try the next one on your own. All I did is change the base to 4. Should still have the same characteristics in terms of intercepts, asymptotes, and domain and range. The only difference is your second point is going to be a different point. It's no longer going to be at 3, 1. So find another point of that graph, connect those 2 points together from your intercept to that point, and then draw the rest. So go ahead and do that, and then when you're ready, press play for the solution. Okay, so I'm going to start off again by drawing the xy plane. And I'm going to do a table of values on the side here. So if I put in x equals 1, that's log base 4 of 1, and 4 to the power of 0 gives us 1. So the point at 1, 0. And then the next one I'm going to try to use is x equals 4. Log base 4 of 4 is 1 because 4 to the power of 1 is 4. So those are my 2 points I'm going to draw. I'm also going to draw my vertical asymptote at x equals 0. Okay, I'm going to connect these 2 points, extend, and then curve our graph towards the asymptote. Should look something like that. Okay, and then for our intercepts, we have an x-intercept at 1, our asymptote is at x equals 0, domain is from 0 to infinity, and then our range is from negative infinity to positive infinity. All right, so that's our basic log graph. Now we're going to look at transformation of logarithms. We are going to follow the same rules we've used from Unit 3 when we learned about transformation of functions. So I'm just going to recap all of that. So the c in front of your log, that's going to be the vertical stretch of a factor of c. This d on the inside of the log that's attached to the x describes the horizontal stretch of a factor of 1 over d. For the h, this means we're translating horizontally from left to right. And then this k, we can move this to the other side as well as plus k if you wanted to. So you would rewrite this as c log base a d x minus h plus k. This plus k means that we're translating our graph vertically, so that's up and down. And we could also reflect in the x-axis when c is negative and reflect in the y-axis when d is negative. So for example 3, I'm just going to create a table values for y equals log base 3 of x and graph the function. We already did that in example 2. So just a really quick draw from what we already covered in example 2. So here is our graph. And if you want to create the table of values, we could go ahead and do that as well. So that covers example 3 part A. Now we're going to graph our transform graph, and we're given y equals log base 3 of 2x plus 6. And then we want to state its characteristics and also describe the transformation in words. Before I go ahead and try to graph this, I need to factor out the 2 with the x, because if you look at the format of transformations, that d here is factored out. So I'm going to factor the 2 out. So we're left with x plus 3. So if I want to describe this in words, this is a horizontal stretch of 1 over 2. And then x plus 3 means we're moving 3 to the left. Again, remember that every time you describe transformations, they have to be in order. So you need to describe the horizontal stretch or the vertical stretch and any reflections prior to describing any translations of moving left, right, up, or down. Okay, so we finished that. Now I'm going to draw my XY plane. And figure out where I'm going to draw my asymptote first. So before we had an asymptote at x equals 0, since I'm moving 3 to the left, I have to move my asymptote 3 to the left. So my new asymptote is going to be at x equals negative 3. And then now I can probably use a table of values to help us figure out what the rest of this graph is going to look like, because we still need specific points for this graph at least. So I'm going to find our next point, which is negative 2.5. The reason why I picked negative 2.5 is because we do need to figure out some sort of number where this is a power of 3. And I'm going to go ahead and show you why I picked this and how it worked out. So after I plug in negative 2.5 into log base 3, I'm going to get log 3 2 times 0.5, which is log base 3 of 1, and we know that 3 to the power of 0 gives us 1. So we have a point at negative 2.50 here, and then we want to find one other point. So we can go ahead and do this again, and I can use a different number. It doesn't really matter which one you choose, but make sure that the inside part of your logarithm is going to work out into powers of 3. And it's going to work out for negative 1.5. Again, I will show you why that's true. That's log base 3, 2 times negative 1.5 plus 3. That's 2 times 1.5 which is log base 3 of 3, and we know that 3 to the power of 1 gives us 3, so we have a point at negative 1.51, and that is enough points for us to finish off our graph. So it's going to go like this, and then towards the asymptote. Try to be careful not touch the asymptote though, just needs to approach it. Something like this. And that is our graph. So before this is over, we still have to describe the intercepts and then state our asymptote, domain, and range. Okay, so then for our x-intercept, that one was negative 2.5. We also have a y-intercept. You can clearly see it crosses the y-axis, so we do need to find that. This occurs when x is 0. So I'm just going to solve for that then. So 2 times 0 plus 6, that's log base 3 of 6. And you would need a calculator to figure out what that number is. So we're just going to leave it like this, or in the change of base formula, which is log 6 over log 3. The next thing we're going to find is its asymptote equation. This occurs at x equals negative 3. And then your domain is from negative 3 to infinity. Your range is from negative infinity to positive infinity.